Great. I'll be doing this with the help of TJ, the software account manager, our friendly and ever helpful support staff that you might have interacted with in the past. I'll start with some slides about VivoQuant, what we've been working on, what we're continuing to work on, some new features in our 3.0 release that many of you have actually started playing around with already. So we have spent a lot of time on our tracer kinetic modeling features in this release, as well as a few new focused clinical workflows and 3D, some of the more popular tools that get used by our users. So I'll just go through them in order here. So in particular with our models, we introduced the tracer modeling package just last year. We've added quite a few new features to it, one of them being information criteria to be used for model selection. So as any of you familiar with modeling might be, it's important to know that mean squared error isn't always the best thing to select which model to use. You can certainly overfit your data, as you can see in this toy example, and it occasionally can be beneficial to minimize something like the Ecrf information criterion or Bayesian information criterion. So the VivoQuant now outputs this with every model that gets run and into spreadsheets, and it shows you in the interface as well. These are just based on standard Gaussian noise assumptions for its computation. The other is weighted fitting, so popular in the tool and can be seen in the literature. The benefit here is really that when you have noisy frames in your dynamic PET image that you're trying to model, you essentially want to downweight frames that have higher variance. You want to give more emphasis to those frames which contain the best SNR, if you will. And to do so, there are a number of new ways to weight those time points. One of them depends on the amount of signal you have in that frame, as well as the isotope decay. So naturally, your signal kind of goes away as your isotope decays over time. And then we also have decay-based correction all on its own. And this introduction is just justified by previous research that from our academic community. In addition, we have a couple new models to the tool. MA1 linear analysis, which is for simple compartmental models, as well as reference tissue, MRTM and MRTM2. So these are new to VivoQuant and are really a great way actually for voxel-wise modeling, if that's something of your interest, in particular for the benefit of its speed. Linear models are very quick to compute. It's a simple regression problem. You can do that at all the voxels of your data relatively quickly. And in particular, in our modeling tools, we put quite a bit of emphasis on performance, and so we do try to get the best speed we can from our tools. In addition, we've added the ability to flexibly fix and/or bound parameters from all of our nonlinear estimation tools. So you kind of see at the bottom here, you can set, for example, fix K4, or choose not to fit it at all. Fix it at 0 if you have a non-reversible model, and then in your two-tissue compartment setup, or do any number of things if you feel that your parameters are going quite out of bounds. Another great addition has been our ability to put functions. In the past, we've kind of put the onus on the user to make sure that that information is pre-processed beforehand and added to a table. Now there's a whole kind of flexible workflow for this. So you can input things like parent and plasma fractions, blood data of different types, and you can smooth it with a sum of exponentials model. You can store all this information to disk as a spreadsheet, and you can iterate, get rid of outliers, do all your sorts of standard processing tasks, and leverage these in your subsequent tracer tissue modeling. The workflow would look something like this. We've, as with many of our VivoQuant workflows, we've designed some of it with the IPACS in mind. If you have an IPACS and can integrate the two together, you kind of get the best of both worlds here. IPACS being a great way to kind of store and organize your data. Here, if you load your image data, compute whether it's your arterial input function or your reference tissue curve, you can store these directly to the IPACS as a spreadsheet, as if it were on your own computer, and then load them back later. They get automatically associated to your image data via its data point framework, and you can retrieve it very easily that way too. In addition, you can visualize previously saved curves, and all these things get stored in the nice session manager in VivoQuant as well. Skipped ahead a little bit. So one more thing, time stability analysis. Won't say too much here, but if you want to run time stability analysis, you can use this to examine the stability of your parameter estimates as you add more and more time points to see whether it was beneficial to have such a long acquisition to begin with, for example, and how robust your parameters are. And lastly, credit to some of our developers, lots of new plotting options to be able to visualize your data, different ROIs together, using different formatting options, and even histograms of the parameters across the entire brain, and bar charts of your different parameters. You can look at your volume of distribution and select a few regions to compare. And they're just neat tools to examine and really drill down on what your modeling has done. So as Christian alluded to earlier, our Ecrf module is new. It's designed with clinical trials in mind. So the idea being that we receive data on the IPACS and want to have a radiologist do some kind of read on it. So the nice thing here that we leverage is that the VivoQuant and IPACS are tightly integrated. So we have, you can set up your kind of form to submit for an Ecrf, either using kind of custom YAML code or a simple form builder where you can provide questions, you can ask them to provide certain metrics or measurements that they've made, and you set this up on the IPACS side. It gets associated to the image, and then you provide a simple setup where you assign a form or a workflow to a particular radiologist reader and say that they're going to fill out this form for these particular scans, and we'd like to get their input on that. And in doing so, the radiologist gets notified of those forms from the IPACS. They can just load up VivoQuant in whatever setup is appropriate. And in VivoQuant, you actually get a little work list of all the different scans that they're supposed to go through. They can go through one by one. And VivoQuant actually has an implemented web browser that renders these forms exactly as you would see them on the IPACS. And so the great thing here, one of the great things here is that it's kind of like all one platform. We really designed this in mind so that you can't make too many mistakes. So I can't load. There's not two software for the forms here and a software for the viewer. I can't load the wrong form or a form for a different patient or something like that. And a lot of these forms contain a lot of validation criteria to make sure that the input that you provide makes sense. If you say yes to this answer, then you can also require the radiologist to provide a comment on why they said yes to that, why they said there are artifacts in this image, what are those about, or a really wide variety of constraints can be placed. In addition, you can you can force them to put in a digital signature to make sure it was them and abide by compliance measures. And lastly, when those forms get submitted on VivoQuant, that information kind of behind the scenes gets stored directly to the IPACs and can be reported on later. So if they go through 8 scans, someone on the administration side of the IPACs just runs a quick report and gets the results of those forms in a quick spreadsheet, maybe with a screenshot, in the flexible IPACs reporting infrastructure to gain all that information in a quick summary. Another addition from our developers is improved data selection. So there are a number of places where data selection was less than optimal in the past in 3.0. So here's a toy example of a dynamic data set with 6 frames. One of the frames has noise, a bunch of random noise, and another has movement. And so if you want to, for example, exclude those in an averaging procedure, it's now very easy. You can have this printer style format of filling out which pages or frames you want to actually select for averaging, and you can select them with checkboxes similarly. There are a lot of nice features in here for power users, like shift select, control select to do quick selections, or drag and drop from the data list so that you can do things really, really quickly. And these are available in now the reorientation operator for reorientation, arithmetics, and the filtering operators as well. We made a number of improvements to the 3D ROI tool. So we've added, we've made kind of some of the things faster. So faster statistics computation and more on-demand computation to improve performance. And we've added some fields that people have requested to add to the quantification form, including things like SUV peak and percentiles of concentration and things like that. And you can always turn these, and now there's a flexible interface for, again, with a similar data selector widget to turn off certain columns and turn them on and control what you want to have in that table very easily. Especially since some of them are more expensive to compute. For instance, the SUV peak can be more computationally intensive. You might want to exclude that if you don't need it, or you might want to include that if it's important to you. The speed of IPACS transfers, in certain edge cases, they can be extremely faster now. That was a collaborative effort between the IPACS and VivoQuant side to improve data transfer of ROIs and general upload of data points from VivoQuant, as well as improved performance on the undo-redo operations, especially with really large data sets where sometimes users would experience slowdowns. We've helped there out quite a bit. And just lastly, a few things up and coming that we've been working on. The modeling tools are certainly a work in progress. They've been designed with a lot of modelers in mind, and we've received a lot of early feedback from them. But we're really excited to see what the greater community does with them and what they see as the next pressing need for them. We certainly have ideas of how we want to enhance it, but we're excited to hear from the community on what they want to see in our next releases. And we really want to improve upon some workflows for computing SUV quantification, making that completely error-free, especially in conjunction with the IPACS, where we can have general ways of storing injected dose information and weight information for each patient, and making sure you don't open or select the wrong numbers from the wrong patient here. If those are associated on the IPACS side on this scanning at time of scan or really early on, then VivoQuant can leverage that information to keep problems away. A number of visualization flexibility for operators seeing ROIs, annotations really across the board and not have them focused on particular operators. New and improved kind of chaining, concatenation, and stacking of transforms in the reorientation tool. And really in collaboration with our team in New Haven, MNI, to to improve clinical trial workflows with VivoQuant and IPACS together. We have some great vision for new segmentation algorithms, particularly for human brain tasks, and quite a few registration improvements that we want to make using some of the state-of-the-art tools that have come out in recent years. So without more delay, I'll let TJ get to the demo. But first, do you have any questions before he gets started? No? Oh, yeah.
Just a quick question. Are any of these features that you alluded to in this dependent upon the flavor of IPACS that you currently employ, or are they just?
Currently, no. So actually, the ECRF was designed for clinical trials, but actually our internal team is using it for rodent imaging trials. It's really a great way to, for example, submit QC forms. We use it for QC workflows. So someone goes through and analyzes all these images, and then a manager creates a form that's intended to be filled out for each image and just gives a little checklist of things that should be QC'd. The alignment looks okay here, the ROIs look okay here, and so someone else goes through and makes sure that those are okay. And it can be used flexibly, and we encourage users to find use cases for it. It's not limited to a particular IPACS installation.
Integration into the larger workflows will be part of the clinical IPACS, but the individual module itself you can use with the discovery.
Yeah. Thanks, Gabe. So building off of Gabe's presentation, I'm just going to quickly go through a live demonstration of some VivoQuant tools, which we're still looking at that. Let's see. There we go. Horrifying. No one wants to see that. So primarily what I'll go through is loading up some dynamic DICOM data, taking a look at some pre-processing, maybe taking a look at the time series to visually see the washout, and then use a brain atlas to really explore the modeling outcome. Let's play again. There we go. So here we have some dynamic DICOM data stored in a local folder. We organize that data based on the DICOM standard. We read the header, parse out the series description, date, time, anything like that that's available, and we can load it right into the software. This is nothing new. We've been doing this really since day one. Here the data load directly into the data manager. You see all the frames will load up. Something that is relatively new, was instituted about a year ago, is we've moved the color palettes here into the data manager. Really a lot of effort in the last year has gone into better handling of these large dynamic data sets. So this was specifically for that, so that we could associate individual frames with their individual color palettes rather than some global setting. So here we have the data. One thing I just want to emphasize is with the time series operator, a very useful tool for viewing dynamic data. So we can set a global minimum and maximum intensity that we're going to use for visualizing all those frames. And maybe you set that max way too low and need to try again. So here you get a nice wash. You can see the curves visually, and then later we'll be able to look at them in the model. The real reason I wanted to run this here was to show right away a lot going on in the striatum. Remember that for later on when we take a look at the curves. You'll see that the quantitative matches the qualitative, which is always what we want to see in imaging, right? And we can, of course, also save that movie directly to a GIF using our handy QC tools. So going into the 3D ROI tool, I'll load an ROI directly from the computer. Again, all of this workflow could be fully integrated with the IPACS. These ROIs can be stored to the IPACS, as many of you know. The data could have come from an IPACS. To be honest, the only reason I didn't use the IPACS was because I wasn't too sure what the Wi-Fi situation would be like today. So far, it's been good, though. So good for the people on the call. Once we have the ROIs into the system, now's the fun part. Now we can view some time activity curves, we can do some modeling. As Gabe pointed out, we've added some new outputs to our quantification table, and you'll also notice this nifty new little dialog here letting you know that you are actually quantifying the data, trying to prevent some crashes that we've seen with really large data. It takes a little bit of time to quantify all these frames. I think here we might be calculating a standard deviation, which is why it's taking so long. The real reason I wanted to pull this up, in this case, many of you are familiar with our quantification table, and one major thing that was improved with this release was that we've added in the time activity curves the actual acquisition time in the x-axis. So the time activity curve is a true time activity curve now. Previously, this would have just said frame 1, frame 2, frame 3, and the curve would have not looked anything like a time activity curve. We've taken care of that now in the 3D ROI tool, so even without the PK modeling plugin, you can still get a nice time activity curve. Or you can do all that through the tool as well. So in the modeling tool, as Gabe mentioned, we've added many models, including our handling of blood input data. So this can be derived either from the image, so an image-derived input function, or we can bring in arterial information or some known plasma data that we pulled from another source. So for instance here, if we want to compute an input function, here we'll just pick a region, the cerebellum. We obviously don't have heart in this image, so we can't get a good blood pool, but we can quickly compute that input function. It's just going to pull directly from the ROI. The times of each frame are stored in the header as this is DICOM data. And then we can choose to run, in this case, a sum of 3 exponentials, fit that curve. Maybe we remove an outlier if we want to. Say this first frame doesn't have any concentration, right? So let's remove that and rerun it. Great. And then we can choose to either save just a linear interpolation between these points or that curve fit. So let's call this the IDIF in this case. So we've just stored that curve fit here into the system. Now I can choose, as Gabe mentioned, to take that curve and save it to the disk, so I can pull it back up again maybe the next time I use this data, or if I have my heart data in a separate image from my brain data and I want to use the image-derived input function separately, I can do that. Or storing again to the IPACS if the data come from an IPACS. I can also load. So for instance, in this case, I've saved up some plasma data. So here it is, and as Gabe pointed out, I can also then view that curve that was ran previously, so I can make sure that curve is still the one I want to go with. Now I've got my blood, I can actually run some models. So this data set works really nicely with a 2-tissue compartment model. I can choose to use my plasma curve. Again, I can read those times directly from the header, and as Gabe said, I can choose to fit or fix any one of the macro parameters. So for instance, or micro parameters, so if I want to set K4 equal to 0, I can do that, set up a non-displaced or a irreversible binding model. In this case, I don't want to actually do that though, so let's fit all of these. And then it's pretty quick. I just click run. Here I'm modeling on the ROI level. You can see that here I can choose to run on the voxel level. That would obviously take a little bit longer, but I can do that as well. I can choose which ROIs I want to look at, maybe one at a time. I can also choose to, that's not a good fit, stick with the straight. I can also choose to store all of these ROIs, all these ROI plots at once, or just one at a time locally. So maybe call that plot 1. I can choose to save my output spreadsheets. And there I get 2 CSVs stored, one with my data and curves for each region, and the other fitting my K1 through K4, as well as my VT, my MSE, my AIC, you name it, which if I just hover over this plot. But that's not new. We've had that for a while. Some interesting tools we've added in this dialogue, though, which Gabe spoke to in his slides, was really adding a lot of flexibility here to be able to view the results of your modeling and really do something with them. So for instance here, I have all of my ROIs and with both their data and their fit, but maybe I'm only interested in the fits, so I turn off the data. Or I'm only interested in the data, so I turn off the fits. Or maybe I'm only interested in a couple of my ROIs, right? I just want to compare, well, what's going on in the striata versus in the pallidum or in the cerebellum, right? I can turn these things on and off. And again, at any time then, zoom in a little bit, at any time I can store with that same save button to the disk exactly what the ROIs or those plots look like at the time, or go to different ones. So let's turn these all back on again. Maybe I want to look at bar charts so I can compare here. Here's my VT across all of my regions. Or if I want to change that parameter, maybe I want to specifically look at K4 to see how much tracer I have coming back. And also the histogram, as Gabe pointed out, so I can see sort of how those values distribute across those various regions. Obviously, if I had more ROIs, maybe I'd have a more uniform distribution here. And of course, we can also, as Gabe said, run all of these on the voxel level. I'm not going to do that today, as there are people planning on talking after me, but if I were to do one of the reference tissue models or a linearized model, that would actually run very quickly, to be honest, and then you can get a nice parametric map, even look at a nice parametric MIP, which can sometimes be a really interesting way of visualizing the distribution of the signal and really getting something quantitative and real out of your data. The one last thing I'll mention is just that everything that I've touched while I've had VivoQuant open is completely open to the VivoScript. So Gabe's going to talk about VivoScripting later on, but one of the real powers of our modeling tool now is it's great that we can run these things once, but we could also choose, okay, I have my one data set, I want to run MRTM, MRTM2, SRTM, SRTM2, 2 tissue, 1 tissue, all of it on this one data set and see that output. That can be scripted up fairly easily using the VivoScript platform, which some of you are familiar with. Or maybe I know I want to run a 2-tissue compartment model, K4 equals 0, I already have all my blood ready to go, batch over a project in the IPACs, come in the next day and have all my model fits ready to go for me. So all of those are options, and this tool is a very good example of a situation to use that tool. So I think that's all the time I have, unless there are any questions. Yep.
2 quick questions.
Sure.
It either happened so fast that I missed it,
Sure.
Or it was already ready to go. How did you get the patient image into the same orientation as those ROIs?
Sure. So here so for the people on the call, the question was about the co-registration of the atlas to the data. In this case, the atlas was already co-registered. However, I could use the reorientation tool or the 3D ROI tool to perform that action. The reorientation tool, I could move the ROI into place, or I could use the 3D ROI tool and manually draw these regions.
And a related question.
Sure.
What if you wanted to draw an ROI on a region of the brain that is not in the template, for example, like the language region of the gray matter?
So
how would you do only that
sure.
hand-drawn region?
The 3D ROI tool is very flexible. In that regard, we have both manual, and it's going to calculate all those again, but manual and automated tools for performing those tasks.
Not limited just to the...
No, this was just one ROI that I had previously segmented and opened up. But certainly you can draw ROIs on the spot, you can run even the Brain Atlas tool and then edit that atlas. It's very flexible in that regard. Any other questions? Is there anything online? No? Great. Well, thank you all very much.